Okay, so I'm Leslie Kelbling. This is the last talk of today. I have to say that I'm assuming that my role here is to be a little bit of a gadfly or a provocateur or something, so don't take me too seriously, but take me a little bit seriously. So I'm interested in how to characterize ways of talking about how well your robot works, and one that we like to say is, well, it probably doesn't suck. So another way of saying that, or another way to talk about the kinds of problems I'm interested in worrying about, is how do you characterize highly suboptimal but still useful robot performance? Like, say, the performance all of you have exhibited today during this conference, right? I would say you probably have been highly suboptimal but still somewhat useful. Okay, so here's my robot, right? I don't always clean the kitchen, but when I do it optimally. So the part of robotics that I want to talk about is like that robot in the kitchen, right? So it's like some real problem in the real world, and it's a big mess, and it's also formally really hard. So almost all the problems that we care about are NP hard, or I mean, that's nice, right? Usually worse than that. And I want to argue somewhat seriously that the fact that the problems we care about are formally hard, right? Or the fact that the problem of that robot in the kitchen, right? That problem is formally really hard, and it's so formally hard that we don't even want to think about it. And I think that's holding us back, right? So I think that there's just a little bit of the looking under the lamppost phenomenon going on, right? So it's hard to prove theorems about that robot cleaning the kitchen, so we look at some other problems that we can prove theorems about. But I want to say, well, what if we know? What if we want to really look at the cleaning the kitchen problem? So the solution concept matters, and I want to tell a story from PAC. So this is the PAC story backstory. So once upon a time in machine learning, this is a true story, learning in the limit was the only solution concept. And learning in the limit says, in the limit of infinite examples, will I eventually find the correct hypothesis? So that was the formal model of learning, machine learning, when I started thinking about machine learning. And the thing about it was that almost every single theorem was negative. No, you can't learn this language. No, you can't learn that language. No, you can't learn regular expressions with this. So there were hardly any positive results. And it was really depressing and demoralizing to do machine learning. And so in '84, Valiant wrote this paper where he said, you know what? You don't actually have to be right all the time. In fact, all you need to say is that with high probability, you'll get an answer which is mostly right. So that let us off the hook in two different ways, right? I didn't always have to get the right answer, and even then the right answer only had to be right some of the time. And that breathed this incredible new life into theoretical machine learning, because now there were actually some positive results to be had. And it's true that we were still proving things about algorithms with big constants and stuff like that, but it was a much more practical view of what was going on. So the question is, what are the appropriate solution concepts in robotics? So I want us to kind of think about that a little bit. And so there's one whole set of solution concepts we're really used to. We want them to be complete or optimal or epsilon optimal. And I'll argue that for problems like cleaning the kitchen, we can't get that. There's another set of concepts which we all talk about: probabilistic completeness, asymptotic optimality, resolution completeness. And so those are theorems, and they're useful. But at least I take from them somewhat cold comfort, right? So in the limit of time, I'll have an optimal solution, but what about tomorrow? Well, okay, so then we can get more concrete. We talk about convergence rates, and those things are more useful. But the question that I wanted to pose, I should say, they asked me to offer a concrete problem, and I said I don't have any concrete. Actually, I have a lot of concrete problems, but I really want to talk about this like big messy problem. And so the question is, what would be good solution concepts for robots like the robot in the kitchen? What's the analog of probably approximately correct for a robot living a long life in a complicated world? And so I would like to have a conversation about that. I'll kind of offer some ideas, which I think are probably not very good, but hopefully to incite angst and discussion. So one idea, which actually I really like, is the idea of bounded optimality. So you could say, well, your robot in the kitchen, of course it can't behave optimally, but it could be optimal subject to the computational constraints of whatever machine it has in its head. And that's actually a really nice framework. It turns out that in some sense, it lets the robot off the hook, so the robot doesn't have to be optimal anymore, so that's good. It puts the theoretician, though, on a super hook, and there's hardly any results that people have in this kind of framework. So it's a nice framework, but hard for the theoretician. Competitive analysis is something that the computer science community has gone a long way with. So I can't be optimal, but can I compete well against some other benchmark? There are things like, well, maybe I just want to say that there's a low probability of killing somebody. Okay, so maybe that's something we could prove about the robot in the kitchen. One thing that I like, and some of us do, is to say, well, maybe I could show it's optimal or something under some assumptions that I know are false, but then try to say something about how false are those assumptions really. So that's kind of an approach. I'm going to come back to this slide in a minute. But I want to ask one more question. And the one more question I want to ask is, what's the role of theory in robotics when this elephant enters the room? Okay, and there's an enormous elephant, which mostly we have ignored. I heard it, a few trumpets this afternoon, and it's the machine learning elephant, right? Okay, so if you haven't noticed, over the last couple of years, machine learning has taken off in a way that it hadn't taken off in a long, long time. And so there's a view that says, oh, to heck with all this algorithms and programming and that stuff. Just make a giant recurrent neural network and shove the input in and see eventually the right outputs will come out. So what about that? So is that going to eat our lunch? Or are we going to embrace it? And if you want to do that, what would you show about it? And will extensive testing suffice in that case? So, okay, anyway, I want to go back to this slide. What do we want to prove about our robots? And if you want to talk about what about algorithms, what about learning, you can talk about that too. So anyway, I'm ready for comments or questions. Okay, stunned silence. Hunger, there we go, yeah.
So the first thought I have, and maybe this is already taken up by competitive analysis, is regret-based methods. Is that very similar to, or is that somehow distinctly different from competitive analysis?
So the question is, what about regret-based methods? I mean, I think, so the thing is, so competitive analysis is the idea that, well, I'm going to try to behave well when I don't know exactly what questions or queries are going to come to me, but then I can compare my behavior against another strategy which knew in advance what the queries would be. So I think that concrete idea of competitive analysis we may not apply exactly, but the idea that we don't hold ourselves up to optimality as an ideal, we hold ourselves up to something else. So regret is regret with, you can't just say, well, usually if you say just regret, you say regret with respect to the optimum. So that's just so that's really trying to optimize, if you want to say, but maybe you say regret with respect to something weaker than the optimal thing. But then the question is, what's a good something weaker to hold ourselves up to?
The other sort of concern I have even proposing that is the notion that, if we're just doing well compared to all the actions we think we could be considering, we get a stock market crash. And so that's sort of a concern in terms of being able to characterize, can we actually avoid that stock market crash or, setting the kitchen on fire?
Right.
So I don't know if it's the right direction, it's just a thought.
Yeah, no, it's a good idea. I think, yep. Oh, they're in charge, I'm sorry.
Sorry, Ross, to cut you off, but actually, so Leslie, I agree with the conclusion that you have on these slides. But the premise I actually have a problem with.
Okay.
So the premise is that we so we're not all academics in this room, but there's sort of two versions of the robotics enterprise. So one is to actually build robots that are self-driving cars and will clean the kitchen, et cetera. And the other is the enterprise, which I think you and I are engaged in more, which is actually not to clean the kitchen, but is actually to understand what it is out of our algorithms to clean the kitchen. And it's probably, you and I are probably not the right people to actually build a robot to clean a kitchen, because they'll do it once, we'll make the video, we'll publish a wait for paper, and we'll move on, right? And that's no good to anybody.
Right.
But what we do is understand what it is about those algorithms. So I think for me, a really good lesson was the RT star, which is that lots of people had looked at different ways of making RT go faster, but this really simple idea of rewiring the RT and to get optimality out of it, all of a sudden everybody understood what it did. The fact that there's a whole bunch of assumptions baked into the RT, sorry Sartosh, that mean it doesn't actually apply to real systems, sorry Sartosh. But still people love it, and it actually, it's because they understand it. So I think that when you talk about theory in robotics, what we're really talking about are what are the bits that we don't understand about the algorithms that are going to let us make progress. And it's less about actually getting the robot to do the thing.
Okay, yeah, I mean, I agree with you, right? This is not so much about getting the robot to do the thing, but
Well,
I
I
would.
don't think it is, and so I think it's important to draw the distinction.
Yeah, no,
Sorry.
okay, but let me see if I can just situate my own concern here, which is, you're right, I am interested in understanding like the underlying principles of intelligent robots and why they can do what they can do and understanding limits and so on. But I would like to address problems that are really big, where I know for sure I can't be optimal or even epsilon optimal, and I would like to not forsake theory. I would like to have a theoretical thing I could say about my system. And I don't have the vocabulary to do that. That's my existential worry.
So I agree with that, but I don't think that we should give up on optimality. So I like the machine learning example. The machine learning example to me is really compelling because they've done exactly the wrong thing. Right? So Dieter Fox has worked really, really hard to convince me that deep learning is something that's really important and really useful. And he's convinced me it's really important and really useful, and he and I should not work on it. And that we should not let our students use deep networks in our research until everybody figures out exactly what it is that they're doing. And he worries that he's turning his students, he said this explicitly, he worries he's turning his students into network engineers and in pursuit of making a product, and that would be a terrible thing for us. So let's keep optimality and figure out the vocabulary instead.
Okay,
I'll stop.
but let's not keep optimality, right? Because I'm not optimal and you're not optimal and none of us are optimal, and yet we don't suck. And the question is, I mean, I think the learning or not learning is orthogonal. I think the question is, what claim do you want to make about a big complicated system in a big complicated world? But okay, someone else should talk.
Leslie's speechless, I like that. So one idea that is not up on this slide is pack. It could be probably approximately clean.
Awesome.
Right? So,
Okay,
but, I mean,
good.
why is pack
Good.
not the right concept for robotics as well?
Okay, that's a very nice idea. So probably approximately clean. So no, that's good. I think one issue that eventually, again, we're all going to have to think about is that the utility functions need to be pretty complicated, right? So as robots become more capable and the things that we ask of them more deep and rich, we also need to say, and don't kill anybody in the process, right? So probably approximately clean is not enough of a spec. But I think that's the right kind of a thing. The right kind of a thing. But maybe we need to kind of elaborate. Yep.
Yeah, so I want to make a comment from my industry experience. I work on self-driving cars, and actually I think what we do is a conjunction of some of these things. We definitely have the low probability of killing someone
I hope so.
Also, we do have a competitive analysis. So for judging whether our system is good enough for doing anything, we want to be able to say we are probably, given the data, 95% confident that we are better than humans, right? Given the data in terms of fatal accidents, not necessarily in terms of comfort or so. But we do have these metrics that we go by in terms of judging our own work. But like, it's not an either-or thing. Like, we use all kinds of optimality algorithms in our algorithms, but we also use machine learning in certain other parts. It's a huge robotics system, of course, a self-driving car. So it's kind of like a combination of everything in some way, right? Yeah.
Yeah, that's good. But the question is, what do you say about it at the most outside level? But those are two good things, right?
Those things.
Yeah, it doesn't kill somebody. Or competitive with human is good. If you're working on a task where competitive human, I mean, so maybe that's a good measure.
So there's a saying that's all models are wrong, but some are useful. And I would venture to say that most cost functions are very wrong, but then some are useful. So, but the thing is, as theoreticians, if you want to prove something theoretical, I think it is a good idea to strive towards some sort of optimality with respect to the wrong cost function. Even though you may have the wrong cost function, it's up to somebody else who's engineering the system and trying to deploy that system in the real world to do the hard evaluation of whether or not the data shows that this does what is, I guess, sellable. That might be the ultimate decision.
But what's the cost? I mean, bounded optimality is the only thing I think we could hope for, right? So optimality is subject to computational resources.
Yeah.
Yeah. Okay. So
Which
yeah.
I think for me that's fine, but I think it's a good idea.
Yeah. So I mean, I love that solution concept. I think it's really cool. People haven't had much traction on that, but I could, people wanted to think about
Well-
that in this community, that would be interesting.
Well, so many people are looking at minimizing path length or minimizing time. Those are obviously the wrong cost functions, but we're striving really hard for it, and we're getting a lot of results from it. I think it helps robots look natural. It helps robots do things more efficiently.
Well, no, but okay, but so let's take the behavior of a robot. So let's take a robot in the world. So not a path, nothing but an objective function on its behavior for some amount of time. So we get to define that objective function, like it cleans the house well, or it doesn't drive over too many people, or whatever, right? So we have an objective function over time, and we have a brain, right? I mean, we have a computer, and we get to put a program in the computer, and we would like to put the best program in that computer we can in order to optimize that objective function. So that's the bounded optimality thing, right? So you won't have time in general to optimize the paths. So that already takes into account the fact that you'd have to back off. So we're used to putting optimality criteria on subproblems, and I guess maybe what I'm asking for here is, what if you had an optimality criterion on the behavior of the thing? And that behavior is made up of all kinds of planning problems and control problems and estimation, and somehow all those things have to add up to performing well in the world, subject to hardware constraints.
Hi, I have a slightly different question. So I'm an investor in a company that actually makes industrial robots that sell these robots to restaurants, and they clean dishes. So their objective function is to break as few dishes as they can. And they use vision, they have an arm, they do a really good job. But they actually found that the driver that led them to break the fewest dishes was not anything in the algorithms, but to design a new kind of a mount so that they found that the human beings loading the dishes into the robot arm were the ones who were breaking the dishes. So they came up with a 3D printed mold that actually let the humans put the dishes in the mold in a simple way, and then the robot took over from there, and they dropped the number of broken dishes by 95%. I don't know how that computes with what kind of optimality that is, but in practical situations, sometimes the solutions are actually by expanding the box of how you define the problem.
Right, so that's good. That's an argument for treating the system jointly, including the hardware and the people it has to work with and so on. Although clearly the way to break the fewest dishes is to not wash any of them. So there must have been another term in the objective function.
Okay, one more question? Yes.
So I come from a machine learning background, and we did a trick in the machine learning community. We rebranded Optimality, and we called it overfitting. And it started becoming a bad word. So there is this general issue of generalization, right? And that's what it's very front and center in machine learning. I find it a lot less front and center in the robotics community. You assume that your model is wrong. You assume that what you're optimizing for is wrong, and that really what you're looking for optimizing in the real world is something slightly different. And being able to measure exactly that gap and analyze that gap and reason around that gap is where the hard work is. And that's why the PAC formulation was so successful, because that's one of the things that it does well.
Okay, well, thank you. So I'd like to thank everyone for participating in this very active discussion. I'd especially like to thank our three open problem presenters, Oren Salzman, Russ Hedrake, and Leslie Kaling. So let's give them one more round of applause. And also to thank the co-organizers of the session, which were Florian Picorni and Yura Vandenberg.
Yeah.
So thank you.